Hello year 10s. In this video I'm going to go through the energy topic end of topic assessment given in class. Let's look at question number 1. A weightlifter picks up a barbell. Which type of energy is stored in the barbell when it is held above the weightlifter's head? Tick one box. Chemical potential, elastic potential, gravitational potential and kinetic energy. So this will be gravitational potential energy. All the students got this right. Next question. The weightlifter drops the barbell. The barbell store of which type of energy increases as the barbell falls? That would be kinetic energy. Next question. 1.3. Use the data in table 1 to draw a line between each calculation and the energy change it is calculating. Draw two lines only. So draw two lines only. Mass of the barbell is 50 kilogram. Gravitational field strength is 9.8. Height of the barbell drops is 2 meters. Maximum speed the barbell drops is 6.2. So that is the mass, gravitational potential, field strength, and the height. That is gravitational potential energy. So, and half mv squared. So this is m, g, and h, and that's half m, v, and v. So v squared. So this would be kinetic energy. So E. Okay. Next question. 1.4. The weightlifter's internal store of energy decreased when he lifted the bar. The bar's internal store of energy increased by a small amount. Explain why. Most of you got these questions wrong because you didn't understand what the question was asking. So they've already stated that the weightlifter's internal energy store decreased and the internal store of energy increased by a small amount. So explain why. What they're asking is, why is there a difference? The main reason is energy is lost to the surroundings. Example, as thermal energy gained by the air. Next question. Question number 2, which is a 6-mark question. You have been asked to find the best material for insulating a hot water tank. For a hot water tank, you have 3 materials: aluminium foil, cotton wool, and expanded polystyrene. Describe an experiment to compare the effectiveness of these materials. Include in your description the way you would use your results to decide the most effective material. So that would be your end point. So that definitely will get 1 mark for you to say that. So how would you do this? The common mistake that most of you made was that you all just repeated that experiment that was done in the class. You need to write an answer which is very specific to the question here. So I'm going to start by drawing a very simple diagram. So I'm going to draw 3 beakers. So aluminium foil, that's for the aluminium foil. This is for the cotton wool. draw another beaker and expanded polystyrene. So let's say I'm going to have 3 beakers that I'm going to use, and I'm going to have a thermometer in each. I'm going to cover that with the that's the aluminium foil, and it's got water in there. That's the cotton wool. The diagrams are not that great on this, but it should give you an idea of what's actually happening. So I've got the insulation. So digital thermometer, right? Let's say 250 ml of hot water, and that will be the insulation. Water in beaker. So the first bullet point, heat a known volume or mass of water to a known temperature. Right? Second, transfer the water to a beaker with the known insulation. Third point, let me bring down the screen so it's easier to write. Cover the beaker with the insulation. So if you're using aluminium, you're going to use aluminium foil to cover the beaker, or if you're using the wool, you're going to cover it with the wool as well. Next, record the temperature and start the timer or stop clock. Fifth point, record the temperature after, I was about to say about, but It's after 10 minutes. Now, most of you made the mistake of just repeating what was done in the class, where you are going to take temperature readings every 30 seconds. That was done to show a pattern. Here, for this question, all we need to do is know the final and the starting temperature. So we don't really have to measure the temperature every 30 seconds. So record the temperature after 10 minutes. Repeat. Using the same mass. The same mass of water with the other insulation materials. Next point. Temperature drop or difference equals initial temperature minus the final temperature. Next point. The insulation with the smallest temperature drop will be the most effective insulation. So you don't really have to talk about a control here as well, where you're not using any insulation, and you don't have to describe that you are measuring the temperature every 30 seconds as well. Next question. Question 3. Figure 3 shows a battery operated remote control car. The car's battery contains a store of energy. As the car moves, energy from one store is transferred to another store. Describe how different stores of energy changes as the car moves. Now, most of the answers that I've seen is actually you describing the energy stores. But what the question is asking, how are these different energy stores actually changing? So we know that there's chemical energy in the battery, right? So most of you have actually pointed that out. There is chemical energy in the battery and there's kinetic energy. But you have failed to actually describe how this actually changes. So the store of chemical energy in the battery decreases while the internal energy or the thermal energy of the surrounding air increases. So I've used these specific words, increases and decreases, to say what happens or how the energy is actually changing. I haven't mentioned kinetic energy here because that's an intermediate energy transfer which eventually is transferred to internal energy of the surrounding air. Next question. 3.2. The car has a top speed of 12 meters per second. So that would be V, and the mass is 800 grams m. Write the equation that links kinetic energy, mass, and speed. Now, a few of you actually failed to write it down as an equation. So writing it simply as half mv squared is not an equation. You are supposed to write an equation. So you need to write either Ke, or in this case, the proper symbol for kinetic energy is Ek. Or you can write it in words: kinetic energy equals mass multiplied by the speed. 3.3. Calculate the maximum kinetic energy of the car. So Ek equals half mv squared. Half is 0.5. Now, common mistake was failing to convert the mass from 800 grams to kilograms. So 800 grams needs to be converted to kilograms. That would be divided by 1000. That will be 0.8 kilogram multiplied by 0.8 times 12 squared. So let's find out what the value is. 0.5 times 0.8 times 12 times 12, or 12 squared. That would give me 57.6 joules. 57.6 joules. Next question. 3.4. Explain why having a more efficient motor increases the top speed of the car. Having a more efficient motor means the proportion of wasted energy is less and a higher proportion of energy is converted into kinetic energy. Or in other case, there's less wasted energy, and which means there's more kinetic energy. Next question. A student investigated the change in temperature when oils of different specific heat capacities were heated. She set up the apparatus as shown in figure 5. So you have a Bunsen burner, tripod, a beaker with water used as a water bath with oil in a boiling tube. This is the method used. Put 25 grams of oil in a boiling tube, pour 100 ml of water into a beaker and heat it with a Bunsen burner. When the water is boiling, put the boiling tube into the beaker. When the temperature of the oil reaches 30, heat for a further 30 seconds and record the rise in temperature. Repeat with different oils. Repeat the whole investigation. Question 4.1. Name two pieces of apparatus the student used that are not shown in figure 5. Now there's a couple of them. So when the temperature of the oil reaches 30, how are you going to actually do that? You will need a thermometer. So thermometer, heat it for a further 30 seconds. There's no mention of a timer. So stopwatch. You could also mention you're trying to pour 100 ml of water. So you could mention a measuring cylinder. And you also mentioned 25 gram of oil. So a weighing scale or a top and balance. Next question. 4.2. What are the independent and dependent variables in the student's investigation? The independent variable is the type of oil used or tested. Not just simply oil, you need to say type of oil. And the dependent variable is the temperature difference or the temperature rise in degrees Celsius. 4.3. Give two safety precautions the student should have taken. Wearing safety goggles. So wear safety goggles. Remember, you need to only give two, not list more than one. But here I'm going to give you a couple of them. So one would be wearing safety goggles, and second is to not heat the oil directly. They're using a water bath, right? Or you could say wear gloves. In brackets you could say hot surface. Next question. Suggest one improvement to the student's method. Because it's 2 marks, you have to give a reason as well. So first point, you could say repeat the experiment. And calculate the mean temperature rise. Or you could say heat the oil for a longer period of time. Why would you do that? To get a wider range of temperatures. Next question. Table 1 shows the student's results with the type of oil listed down, and the temperature rise in degrees Celsius. So they have done it 3 times and they've calculated a mean, and there's one value which is missing here. Calculate the mean temperature rise for olive oil. So for olive oil, they're asking you to calculate the mean. How do you calculate the mean? Give your answer to 2 significant figures. Some of you didn't read that sentence properly, so you add all these 3 values up: 17, 17 and 18. So 17 plus 17 plus 18, divide that by 3. So 17 plus 17 plus 18, that gives you 52. Divide by 3, that gives you 17.3. 17.33 reoccurring. So because they're asking you to give it in 2 significant figures, the answer is going to be just 17. Next question. 4.6. The mean change in temperature of the castor oil is 20 degrees. So that's the change in temperature. The specific heat capacity is 1800 joules per kilogram degree Celsius. So that's the specific heat capacity. The mass of the oil is 0.025 kilogram. Calculate the change in thermal energy of the castor oil the student used. Use the correct equation. So the equation is the change in thermal energy, delta E, equals the mass specific heat capacity multiplied by the temperature change. Mass is 0.025 multiplied by 1800, multiply that by 20. 0.025 multiplied by 1800 multiplied by 20, that gives me 900. So the change in energy is 900. The unit will be, because it's energy, it will be joules. Next question. Question number 5. Figure 6 shows a kettle as a student used to determine the specific heat capacity of water. The student placed different masses of water into the kettle and timed how long it took for the water to reach boiling point. Now, to reach boiling point, that would be 100 degrees Celsius. The student carried out the experiment 3 times. The student's results are shown in table 2. So let's have a look at table 2 properly. So you have different masses going up in 250 grams increments, starting at 250 grams or 0.25 kilogram, going all the way up to 1.75 kilogram. There's a mean missing there, and the energy supplied is also missing. So when you look at the table, most probably you're going to have questions asking you to calculate the mean and the energy supplied in the follow-up question. So 5.1, suggest how the student was able to ensure that the change in temperature was the same for each mass of water. What they're asking, how can you make sure that you're heating the water for the same amount every single time? So you could state that, first point, water boils at the same temperature each time. That would be 100 degrees Celsius. Because you want to make sure that the change in temperature was the same, so the end temperature is going to be at 100 degrees Celsius because it's boiling at 100 degrees Celsius. Second point is to say, how are you going to make sure that it starts at the same temperature? You control the starting temperature by allowing enough time for water and kettle to reach room temperature. So you don't simply do the first test and then get rid of the water and add more water for the second test. You allow enough time for it to reach the room temperature, which should roughly be stable every single time. Next question. 5.2. Calculate the uncertainty in the student's measurement of time to boil when the mass of water was 1.75 kilogram. So most of you got this wrong, mainly because you didn't know how to calculate the uncertainty, right? But I think one person actually did get it right, which is actually good. How do you calculate the uncertainty? When you look at the figures for 1.75, you find the lowest and the highest numbers, which is 298 and 302. So you take away, you find the uncertainty. You take away from the highest number, the lowest number, 298, which is going to be 4, and then you divide it by 2, and that gives you plus or minus 2. So uncertainty is given, right? Plus or minus. You don't really need the plus and minus signs here to get the marks, but so from the mean value, either it can be plus or minus 2 in terms of the measurement that you're making. The power rating of the kettle is 2.2 kilowatts. Question 5.3. Calculate the average electrical energy used by the kettle in kilojoules for 1.75 kilogram of water to reach boiling point. So the equation is energy transferred equals power multiplied by the time. This comes from the equation power equals energy transferred divided by the time. So the power is 2.2 multiplied by 300. Where am I getting 300 from? If I find the mean for 1.75, it's going to be 300. So the mean would be 300 there. That gives me 660 kilojoules. 5.4. Use information from table 2 to calculate the change in temperature of the water during the investigation. So the change in temperature of the water during the investigation can be calculated from using the value that is given. So they have already given you the mass times the change in temperature. This we can get it from the table, and we can divide that by the mass. So if I look at the value, going back to the table, these values, so mass multiplied by change in temperature, and I'm going to use this value 0.25. So 20 divided by 0.25, 20 divided by 0.25 will give me 80. I can use any of the values from the table where they have already given me the values. Next question. The student plotted a graph of energy supplied in kilojoules against mass times change in temperature. Figure 7 shows the graph the student plotted. So they've already plotted 3 points here, and they're expecting us to plot the rest of the points. Use data from table 2 to plot the 4 missing points. So let's have a look at the 4 missing points. So we need it for 80 onwards. So at 80 degrees, it's about 401. Now you can see that there's 5 boxes, so each box is about 20. So this is going to be a rough estimate. That's 401, 470. So 420, 440, 460. Oops, sorry, I'm looking at 400, 440, 460, 470 is going to be there, and 580 is 420. So 580 should be there, and the last one, 440, is going to be 660, what we actually calculated. Now you should be able to draw a straight line of best fit, and that line will not actually go through 0. If it goes through 0, then you're actually trying to manipulate the line, so it doesn't have to go through 0. The reason, at the start, that will be the room temperature. So when you draw a straight line, let me see if I can draw a straight line in here. So line of best fit will start from there, roughly. Oops, oh, that didn't work out. Hold on. Didn't want to draw a square. So there, and the straight line like that. So 2 marks for getting the all 4 of the points plotted correctly, and 1 mark for a straight line using a ruler. Next question. So how do you use the graph to determine the mean value of the specific heat capacity of water from the student's investigation? Remember the equation. Delta E equals MC, which is the specific heat capacity that we are trying to find, multiplied by the temperature change. So rearranging that equation, delta, no, sorry, C, specific heat capacity, is the energy transfer divided by the mass times the temperature change, which is actually the gradient of the graph, y divided by x. So we can find the y and x values from the graph. So if I look at the graph back again, I'm going to read off this value. Say, let's say, take that as 50, and that would be 660. So the difference is 660 minus 50. That gives me 610. Remember, this is in kilojoules. So if I multiply that by 1,000, that will give me 610,000 joules. Now the x value is going to be up to 140. So going back, 610,000 divided by 140. So 610,000 divided by 140 gives me 4,357.14. I can round it off to 4,357 joules per kilogram degree Celsius. As long as your answer is between 4,200 to 4,800, you will get all 4 marks. Question 5.7. The student's value for the specific heat capacity of water was greater than the accepted value. Suggest why. The answer is usually going to be bigger because some of the energy supplied does not raise the temperature of the water. Why? It's wasted or lost to the surroundings. But for 1 mark, you just need to say some of the energy does not raise the temperature of the water. Next question. The kettle used in the experiment had a label stating that the power rating of the kettle was 2.2 kilowatts. The student did not measure the power of the kettle. Suggest why measuring the power of the kettle may improve the student's investigation. Although kettles, they actually give a rough value. So the power may not be 2.2 kilowatts exactly. Right? Or you could say, by measuring the power, the student can accurately calculate the amount of energy supplied to each mass of water. That brings us to the end of the questions. Watch the video, use a green pen to make the corrections, and bring your test papers to the class. Thank you.